couple of brief comments, mainly related to the problem set that you had for homework tonight. If you want to solve an equation like x to the 2/3 equals 7, that's an x to the p equals some number, you take the 1 over p power of both sides. Now the reciprocal of the 2/3, the 1 over p if p is 2/3, is clearly going to be 3/2. So we take the 3/2 power of both sides, we get x to the 2/3 raised to the 3/2 equals 7 raised to the 3/2. Now the 3/2 power of the 2/3 power, we multiply exponents, we have x to the 2/3 times 3/2 equals 7 to the 3/2. And 2/3 times 3/2 is 1, so we have x to the 1 equals 7 to the 3/2, or x equals 7 to the 3/2. An unrelated comment, again just reviewing something that you might need for the homework assignment, is if we have a sequence S formed from a quadratic function. Now this sequence is the squares of the numbers 10, 9, 8, 7, 6 squared, so it's clearly quadratic. The first difference of this function, well, 181 is a difference of -19, 81 to 64, difference is -17, and so forth. Now there's a clear linear progression to this first difference, and the second difference is a non-zero constant. Second difference, of course, these numbers are increasing by 2 each time. This is a property of quadratic functions. If the second difference is a non-zero constant, then you have a quadratic function with a non-zero coefficient of x squared that generates your original function. And of course there'll be a linear function that generates your first difference. This can be generalized if it takes 6 differences. If you've got to go to s prime, 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 the 6th difference before you get a non-zero constant, then you had a 6th degree polynomial to generate the original. Okay? And differences to a non-zero constant means that you have an nth degree polynomial, or there is an nth degree polynomial that will generate your sequence.